Welcome back to PixelPromenade Intersections, bridging boundaries, co-creating tomorrow. I'm Nico Marzian, your host, and thank you for joining me again today. The previous episodes in this series have been about collaboration problems that play out in cities, in value chains, in landscapes. The stakes in each are high, the condition of our urban infrastructure, the transparency of what we make and how we make it, the health of the ecosystems we depend on. These are not small things, but the governance decisions in those domains share one important characteristic. When they go wrong, the window to course correct remains open. A failed logistics zone can be redesigned. A value chain that was never designed as a whole can begin to be designed. A degraded landscape can, with the right conditions, begin to regenerate. This episode is about a collaboration problem that plays out in orbit. The actors are fewer, but more powerful. The stakes are high, and in one critical respect, not recoverable. Orbital debris, once generated at sufficient density, cannot be recalled. The Kessler cascade, the chain reaction in which collisions generate fragments that cause more collisions, is a one-way door. Once through it, the orbits that underpin global navigation, communications, climate monitoring, and financial infrastructure become unusable for generations. That is the outer boundary of the conversation. The inner boundary, where we actually are right now, is considerably more optimistic. We are at the moment when space stops being a domain of scientific exploration and government programs alone, and becomes something else, an industrial environment. And that transition is happening faster than almost anyone predicted, driven by signals that were not present even 5 years ago. Before the signals, it is worth pausing on the idea, because the strategic logic of moving industrial activity to space is not new. It is at least half a century old, and the person who articulated it most clearly was not a technology entrepreneur. He was a Princeton physicist named Gerard K. O'Neill. Professor O'Neill's book, The High Frontier, published in 1977, made an argument that was then considered eccentric and is now looking increasingly prescient. That the fundamental problem facing human civilization is not a technology problem, but a space problem. Not outer space, physical space, room, resources, the capacity to expand industrial activity without further degrading the planetary systems that sustain life. His proposed response was to move the most resource-intensive and pollution-generating industrial processes off the Earth's surface entirely, into space, where the resources are effectively unlimited, the solar energy is uninterrupted, and the ecosphere that biological life depends on is not at risk. Dr. Philip Metzger, planetary physicist, co-founder of NASA's SwampWorks at Kennedy Space Center, and as a leading researcher now at the Florida Space Institute, I've had the privilege of engaging with directly through my roles at Earthlight Foundation's New Worlds Institute, has spent much of his career working out how O'Neill's vision could actually be bootstrapped. His modeling, published in peer-reviewed aerospace engineering journals, suggests that a self-sustaining, self-expanding robotic industrial system in space is achievable with as little as 12 metric tons of seed hardware landed on the moon over 2 decades, growing exponentially from there, powered by in situ resources, until the industrial capacity available to humanity exceeds anything constrained by a single planet. The primary challenge Metzger identifies is not technical feasibility and not cost. It is persuading people that it is not a fantasy. That has always been the governance and communication problem at the heart of this vision. The signals that would have seemed improbable when O'Neill was writing are now arriving in rapid succession. Space-based data centers have moved from concept to operational hardware within the past 12 months. In November 2025, StarCloud, a startup that reached unicorn status in 17 months after Y Combinator Demo Day, launched the first commercial satellite carrying an NVIDIA H100 GPU. They used it to train a language model in orbit, the first time this had been done. In January 2026, Axiom Space launched its first 2 orbital data center nodes into low Earth orbit. In the same month, SpaceX filed a request with the Federal Communications Commission for permission to launch a constellation of 1 million satellites for distributed compute in orbit. Google's CEO has described space-based data centers as the new normal within a decade. The structural logic is compelling. Terrestrial data centers are running into hard physical limits: power, cooling, land, and community opposition. AI computing is projected to consume 12% of US electricity by 2028. Solar irradiance in orbit is 36% higher than on the Earth's surface, available without atmospheric interference, without weather, and at near zero cost once the infrastructure is in place. Radiative cooling in the shadow of the Earth approaches absolute zero. One analysis suggests that at launch costs of $200 per kilogram to low Earth orbit, the threshold SpaceX Starship program is targeting, the economics of orbital data centers become competitive with terrestrial alternatives. We are not there yet, but the trajectory is clear. In-space manufacturing is the deeper signal. The International Space Station has already demonstrated that microgravity enables the production of materials that are structurally impossible to create under terrestrial gravity. Fiber optic cables with fewer defects. Pharmaceutical compounds with superior molecular structures. Semiconductor crystals without the imperfections introduced by the gravitational stress that is inescapable on Earth's surface. In February 2025, ESA published studies confirming that in-orbit refurbishment, manufacturing, and recycling are viable options, not merely theoretical propositions. New ventures are beginning to build the cargo return infrastructure that would make orbital manufacturing commercially practical. Dedicated re-entry vehicles, uncrewed space stations, autonomous logistics chains between orbit and ground, and even the means for spacecraft refueling, in-orbit servicing, and orbit correction to extend the life of facilities in space. And the debris remediation signal is the one that shows the governance problem most clearly. Capture technologies have been demonstrated in orbit before: nets, harpoons, drag sail, but only on purpose-built test objects deployed by the same missions. No actual piece of pre-existing debris has ever been actively removed from orbit in a controlled manner. That is about to change. Astroscale's ELSA-M mission, scheduled for 2026, will attempt to remove a prepared satellite equipped with a compatible docking interface. ClearSpace 1, also targeting 2026, will attempt to capture ESA's own Proba 1 satellite using a robotic 4-armed gripper. A known, characterized object, but the first time a real piece of hardware will be actively retrieved. These are not yet missions targeting uncontrolled, uncooperative debris, but they are the essential first step toward that capability. ESA has committed to a zero debris policy by 2030. The FCC has tightened deorbit rules, requiring operators to remove satellites within 5 years of mission end, down from 25. These are the first governance signals that the shared orbital environment is being treated as shared infrastructure requiring collective stewardship rather than as open sky to be used without accountability. The analogy I find most useful for understanding where space governance is now is the high seas. For centuries, the oceans were effectively ungoverned, a frontier that competing nations treated as an extension of their own interests, a commons that nobody was responsible for protecting. The consequences were predictable: overfishing, pollution, conflict, and the progressive degradation of a shared resource that everyone depended on. The international frameworks that eventually emerged, UNCLOS, regional fisheries agreements, maritime pollution conventions, were imperfect, contested, and arrived later than they should have. But they created the basis for collective stewardship of a domain that no single actor could govern alone. Space is following a recognizable version of the same trajectory, at a faster pace and with less room for error. The Outer Space Treaty of 1967 was written for a world in which a handful of governments were the only actors in orbit. It never addressed commercial or private activity at all, a gap that has been actively contested for the past 15 to 20 years without resolution. National legislation in the United States, Luxembourg, and elsewhere has attempted to fill parts of that gap, but international consensus on property rights, liability, and the governance of commercial space operations remains absent, and the geopolitical context has shifted dramatically. Space is no longer only a domain of scientific cooperation and national prestige. It is a contested, dual-use environment. Satellites serve civilian and military functions simultaneously. Anti-satellite capabilities are being developed and tested by multiple powers. And the militarization of orbital infrastructure is accelerating. The governance framework that exists was not designed for this level of complexity, this speed of change, or this degree of geopolitical tension, despite having been written in the era of the Cold War. The collaboration problem in space governance is structural. The orbital environment is a shared resource. Debris generated by one actor damages the operating environment of every other actor. The benefits of clean, accessible orbits are collective, but the costs of maintaining that environment, compliance with deorbit rules, investment in debris remediation technology, restraint in constellation deployment, fall on individual actors who have competitive incentives to free-ride. This is precisely the tragedy of the commons, operating at planetary scale. What the debris remediation missions being funded and planned right now represent is the first serious attempt to treat orbital cleanup as a public infrastructure problem rather than a voluntary act of good citizenship. The shift in framing from individual compliance to collective governance is the same shift that every domain in this series has needed. And it is arriving in space at the same moment that the economic value of the orbital environment is becoming large enough to make its degradation genuinely catastrophic. In the near term, the next 5 to 10 years, the picture is one of accelerating capability and lagging governance. Orbital data centers will scale from demonstrators to operational infrastructure. In-space manufacturing will move from pilot to early commercial operations, beginning with the highest value materials, those where microgravity's advantage is large enough to justify the logistics. Debris remediation will graduate from demonstration missions to contracted services. Launch costs will continue to fall as reusable heavy lift vehicles scale and lifetime extend, and lifetime value of in-space facilities grow thanks to spacecraft refueling, in-orbit servicing, and orbit correction. The collaboration architecture that will determine whether this scales well or badly is being built right now in the regulatory filings and governance negotiations that rarely make headlines. Who has the right to occupy which orbital slots? Who is responsible for removing debris objects of disputed or unclear nationality? How are the benefits of space-based data infrastructure shared across nations with vastly different access to launch capability? How does the intellectual property generated by in-space manufacturing get governed across jurisdictions that have no common framework for it? Beyond the next decade, the vision that Metzger's modeling and O'Neill's original argument point toward is more radical. A self-sustaining industrial civilization in space that draws on the resources of the solar system, lunar regolith, asteroids, the abundant energy of an unfiltered sun, and returns value to Earth in the form of clean energy, materials, and the freedom to use the Earth's surface for what it is uniquely suited for. Living, growing, regenerating. The bootstrapping process Metzger describes is not a fantasy. It is an engineering program with a credible roadmap, a growing industrial base, and a strategic logic that becomes more compelling the further terrestrial civilization pushes against the limits of a single planet. It is worth being precise about something before we close. NewSpace is not simply a fourth domain alongside urban mobility, manufacturing, and regenerative sustainability. It is the layer beneath, or better, above them. The infrastructure on which several of the other domains already depend, and on which more of them will depend as the decade progresses. The navigation infrastructure that makes V2X and seamless urban mobility possible is satellite-based. The Earth observation data that provides the only credible verification layer for regenerative outcomes at landscape scale, soil, carbon, land use change, ecosystem health, comes from orbit. The supply chain monitoring that will make digital product passports meaningful beyond a single jurisdiction requires satellite coverage. And the in-space manufacturing capabilities beginning to emerge will eventually produce materials, advanced semiconductors, pharmaceutical compounds, optical fibers that re-enter the terrestrial value chain in ways we are only beginning to map. This is what O'Neill understood and what Metzger's work makes concrete. The long-term logic of moving industry to space is not about abandoning Earth. It is about relieving it, freeing the planet's surface from the industrial processes that stress it most, while returning value in the form of energy, materials, and the monitoring capability to understand and restore what has been depleted. Space is not an escape from the problems of the other domains. It is, at the right scale and with the right governance, one of the conditions for solving them. So, I want to close this episode and this phase of the series by naming something that has been present in every domain we have covered. In urban mobility, the collaboration problem was between actors sharing the same physical infrastructure, each optimizing for their own domain, none optimizing for the system. In digital manufacturing, it was between actors across value chain that was never designed as a whole, assembled from bilateral relationships and data silos, with the insight eventually arriving that value no longer lives in any single node, but in how the entire chain performs. In regenerative sustainability, it was between actors managing interconnected natural systems under separate institutional mandates, unable to see the synergies that only become visible at the level of the landscape. And in NewSpace, it is between actors sharing an orbital environment under a governance framework that was never designed for them, in a geopolitical context that is becoming more contested, not less. The structural pattern is identical in each case. The system is more complex than any single actor can comprehend from their own position. The outcomes that matter, efficient cities, transparent supply chains, regenerating landscapes, accessible orbits, merge only when actors coordinate across the boundaries that separate their domains. And the collaboration infrastructure to make that coordination possible, the shared environment, the human bridging function, the intelligence layer, the mechanism for equitable value exchange, is what is missing in every case. That is not a coincidence. It is the central problem and challenge of our moment. And it is, in each domain, a solvable one. Thank you for watching. For now, please take care, and I will see you next time. Goodbye.